Good morning, everyone. So we are starting. I'm just giving 2 or 3 small words about practical information of today. I ask for everyone to close their mic and even their video during the presentation because for the stability it could be better. We have a list of the participants that will be at your disposal in the chat room. The chat room that you can use for the questions for the speakers. If we have time, you can as well raise hands, but it's more easy if you use the chat room to ask your question over there. And we will play this role today to pick the question and to make the Q&A session. This webinar will be registered. You will have all the presentation afterwards. Really, I really want to thank you, the host EnergyVille of today, especially Nathalie Benmans, that have done a lot of work with our team to make it happen. Really, thank you. Because it's very important, this link between the 2 regions in this very important topic, the storage. And it's quite difficult right nowadays to organize something. Of course, it would be better with a coffee and to be together, really. But still, we make it happen virtually. And so really, thank you for the time of the EnergyVille team and for the hosting of today's meeting. So I let the floor to Ronnie Belmans, the CEO of EnergyVille, right now for this very interesting day. Thank you to everybody and have a good webinar.
Thank you, Cedric. I hope you can hear me. Welcome everybody, although it's a very weird welcome. I would have loved there would not only have been coffee, but also the marvelous Limburg Vlaai that would be there, but we will keep the idea for next time. We won't keep the Vlaai because it won't take that long. Welcome at EnergyVille. You see the program here. I'm going to give you an introduction of roughly ½ an hour to EnergyVille. Then Johan Riesen is going to talk to you on DC grid, DC power. Then we're going to have battery materials, so from the material by Philip Peters. Then we go to the management system of the batteries, and this is Cedric, very good to have such visits, and that's why the welcome is from both. It's really also to our benefits. Yes, we will have the tour of the laboratories with the virtual tour, which is not so good as the real tour, but being forced by COVID and trying to accommodate this for us also a very important visit, we really worked on those tours, and they would never have been finished on such a short time than if there would not have been your visit. So every problem is a challenge and brings out the best in people to do that. Please have your questions ready in the chat. We will try to answer them. The thing is recorded. If you have later on questions, email them to the info at EnergyVille or communications at energyville.be. We will answer them. This is an open center. We accommodate the people where we have where we can, and we try to make things move ahead. So let's look at a short presentation on EnergyVille. We all know what the problems are. The challenges are clear. The world is changing. We are going to get a double amount of people, and they will use much more energy. But we have to do that in a sustainable way. And then we go to the distributed system of the future. I don't have to talk through this in a detailed way, but for us, there are a number of things which are happening there, and which is, of course, the electrification of whatever is possible. And a lot of the work is electrical, but also the thermal networks. Just before this seminar started, we had discussion with the colleagues of Cluster TWEED saying that there will be at the Valson-Lambert site, there will be a thermal heat network where we can collaborate on. So we have the thermal energy that can be used, for instance, as a storage device for electricity, but also we need sustainable molecules. Part of it being hydrogen, but also other parts being methanol, methane, etc. So this is where we are working on. And dear friends, let's be clear, what the Commission has said now, being 50 to 55% of CO2 reduction by 2030, which will mean more than the clean energy package, which stated 32% coming from renewables. It probably will end up with 40 to 45% of the energy coming from renewables by 2030, which will lead probably to more than 2/3 of the electrical energy coming from renewables within 10 years. So the whole debate in Belgium of how many percentage X and Y we are going to have is a very fertile debate. The thing is, let's work on it and see that we can get to that 2/3 of renewable energy in 10 years. This is a challenge that in my long career has never been raised by the politicians to our sector. So really, it's a very major challenge. We have to do something about it. We have to look also at the energy efficiency. And we are going from that classical model, we all know, to a new model with a lot of energy vectors, but also a lot of data. And I don't have to bring you in detail on that. But if you go to the overall idea, you see that the energy system, which was before, in fact, you get 3 energy bills at home every month, or every 3 months, or every day partially, being the energy bill for the car, the energy bill for the heating, and the energy bill for the electricity. Those 3 energy bills will be brought into one. We will get energy probably as a service, like we do with communication, and how it is brought to our house with direct current, with heat, whether it's done in cars, whether it's done, whether it's generated locally, you don't care. It's really an energy system which is transparent for the user and gives comfort to the user. By the way, just made yesterday as an example, a small calculation. The EU is thinking that by 2030, there will be 35 million electric vehicles in Europe. Let's hope that it does. And then we have, if you made a calculation with 50 kilowatt hours of storage in each of those electric vehicles, you have 1.7 terawatt hour of daily storage, over-day storage available only in those vehicles. How to handle that, how to work with that, we don't know. And that's what we are working on. So we go from a demand-driven generation system. When you get more demand, the power plant delivered more, the good old days, the way I started my career. And we go now to a system where we have really energy, which is generation is driving demand. How is the demand going to change if there is sun, if there is wind? How is the heat going to be integrated in that? Can we have heat storage with new companies that control that heat storage? How is it done? How is it done that vehicles are charged and discharged to balance the whole system? For us, we are a societal driven research institute. And for us, the idea is that the citizen has to carry the idea of the energy transition. But the citizen, and we all are citizens, but we are special ones, we are in this business. And business being research, being also business like with companies, but also my colleague researchers in the universities in Wallonia. And we are interested in the climate and the whole problem, but in fact, society is not. Society, people are interested in their living environment, the inner circle of concern. And then there is a visible, tangible energy circle, which are high voltage lines, wind turbines, highways, and that kind of stuff. And you don't want to be in there because people are complaining. We are not going to talk about high voltage lines like Ventilus in the booklet du Hainaut, but these are things which are not, people know that they need it, but they don't want it. We have to show that the energy transition is within their living environment and offers them more comfort. I don't want to hear the word that the energy transition will restrict people in doing things. With the energy transition, we will offer more comfortable technologies like electric vehicles, heat pumps, silent, no local environmental problems, no dust, no smell. That's the new society we are going to. And this is what we are working on all together. So the vision is clear for EnergyVille. We have the IoT, a lot of data. We have distributed energy. We have heat. We have molecules. And we want to make it an affordable, sustainable, reliable energy system. And we are a top research center to collaborate to enable a transition towards a market-based, sustainable energy system. And here I want to make a small parenthesis, but a very important one for you. EnergyVille, certainly I know that there are a number of my colleagues on the quote-unquote line here. EnergyVille is an open society. If you think after today and later on with other subjects that, for instance, some of your PhD students can benefit from a stay at EnergyVille, for a collaboration in EnergyVille, from tests being done at EnergyVille, please let us know. We are open, and I always say, and I repeat it, the closest engineering faculty to EnergyVille is Sartillement in Liège, and not Leuven. So it's even downhill to come there. So be welcome. I know that a number of you are already collaborating in a number of projects with some of my colleagues. So let's continue that. Let's have a big round of Belgian young engineering professionals that work on top things all together. Too much to do to double, to put effort in the same thing that have already been done at another place. So we are a top research center. We have four people, four groups that have invested in it. KU Leuven, University of Hasselt, IMEC and Vito, and we are working together at one place. This is unique in Europe that two research institutes and two universities have joined their energy research and brought their people together at one place. It's not a virtual institute, it is there. We are doing basic, applied and industry-driven research at one place, theory and experimental. You will see later on what we have as experimental things, and really have a look whether we can collaborate on that. We need brains, and we need the investments that we are doing used as well, as efficient as possible. We develop materials, technologies, and methodologies. We are going for new products and services. That's the good thing of being together with Vito and IMEC as universities, that the transition from basic research to applied research to companies is much faster than before. And we are assisting in human capital development. The energy transition will be stopped by the lack of personnel, human capital, technicians, but also engineering, economists, and all the stuff. We need good people. And we are given science-based policy input from local level to global level with reports that you probably may have been reading. Here you see the same slide as before, but now colored. None of the subjects we are researching on, which you see here, is only with one of the partners. For instance, if you look at if you look at strategies and market, it's Vito, KU Leuven, that's working on that. If you look at building integrated PV, it's KU Leuven, IMEC, University of Hasselt working on that. So it's always a collaboration. And this is what makes things so interesting. It's unfortunate that you cannot visit the building, but otherwise you would see that we have open desk policy where people from the 4 institutes are working together in a room on a certain subject. This is what we are. If people are asking how many persons are working at EnergyVille, my answer is I never know. I hope they all are, but that you're never sure. But there are 406 badges, 406 people that can enter the building to do work. There are 42 nationalities, and of the 406, there are 165 PhDs. Here is what you would have seen, you would have not been in a drone, but what the site looks like. At the right-hand side, you see incubator, the white building, which is a building where 700 people are working now for startup companies. It's incubator. I will say later why. We have EnergyVille 1, the building you will visit also later on, being it via the computer, EnergyVille 2. And in front, we have the old mining building. The front building is the compressor building and the building for the motors. No, sorry, the building for the motors for the mining lift. Then you have the mining lift. And further to the left, you would see the big old renovated mining building. Just for your knowledge, there's also T² a bit further on, where there is secondary schooling and schooling for people, retraining of people, roughly 12 to 1,300 people there. On the site, there are roughly 2,000 people walking around, being there at the moment. It's going to be growing. CMI, Cochrane, is investing also in a new building together with LRM on Industry 4.0. So the place is booming, I think so. And if you would have been there 5 years ago, except for the old to-be renovated buildings, nothing was there. Everything is built over the last 5 years. So if they tell that China can do things much faster, that's true. But this thing is also quite impressive to my feeling of what we, with a lot of people, brought there together. For your information, in the investment of the buildings, there is no European, there is no Flemish money involved. It's all have been invested by Vito, IMEC, KU Leuven, University of Hasselt, LRM, and NUMA, a local, and the provincial investment company. We'll flip to it quite fast, but you will see that here you get the first view on what we do as laboratories. We have a laboratory on material and devices with thin film PV lab, the PV solar cell lab, the module lab that's around, lab on reliability, and we don't make a distinction between EnergyVille 1 and EnergyVille 2. This, for instance, in EnergyVille 1, the previous one were in EnergyVille 2. We have the octobre PV lab, which is on EnergyVille 1, metrology, again, 1, and you see here then the battery lab, dry lab for batteries, interfacing lab, and the wind tunnel, then the design of organic semiconductors and also perovskites, design and synthesis of inorganic materials. Some of the labs are still in Hasselt and also at IMEC, but they are moving. Then you have the system labs, the material labs for batteries you've seen already. Here you have the testing lab, which is now being enlarged, and I think that the movie you will see later on, the visit you will have later on, already shows the new lab. This is the home lab, where we work with intelligent appliances, low voltage lab, thermal, medium voltage, the PV integration lab on EnergyVille 2, the DC lab, one of a unique lab in Europe, being totally ready for real applications on low voltage home DC. And then the power electronics lab, grid emulation. To give you an example, we were the first lab to test the relay on HVDC for Mitsubishi. We're collaborating with a number of companies. And then we have here the smart charging lab, where we use our own vehicles to really play around with what we're doing in charging. For instance, intelligent charging, where the vehicles are charged with respect to your own calendar and the time you're leaving for home. So this building itself is a lab. All the labs you have seen are linked to each other. So we can have, for instance, a smart charging lab being supplied by the PV on the roof, by a DC, looking at the same time being linked to the batteries. And so you have a lab of labs being the building itself. And the building itself, we are doing an awful lot of research also on energy in buildings. Energy in buildings, and I told you with the comfort being one of the major aims of the energy transition, we have made the challenge, we have taken on the challenge to really see whether we can live to our own words, that we could walk the talk. And EnergyVille 1 has been built to the BREEAM standard. And BREEAM is a British standard that stands for environmentally friendly buildings, energy efficient buildings, with a high level of comfort for the people that are working there. So, and if you look at the whole, what's in the building, you have to look at the water consumption. People have to be able to charge vehicles. There has to be room for bikes. There has to be, during construction, you have to look at the waste treatment. And we were very scared. But at the end of the day, like a student, you go to BREEAM, you ask, is the design okay? And we got excellent for the design. And then if you go to the end, when the construction is done, they come in to have a check. You are checked continuously. You have to give data in continuously. And we got the highest certificate outstanding in the post-construction, and it's still monitored. So yes, we walk the talk, and we are proud of that. And that building is, is working as we think that building should work. And if we ask our collaborators, maybe they are polite to me and don't want to say the truth, but working there is fun. Getting there sometimes is more difficult. So we have the laboratories, we have the building as a laboratory of the laboratories, and we are extending that. We have the ecosystem, the whole Thor Park. For your information, Thor stands for the Norwegian god that brought the energy to the world. But Thor locally stands for the old soccer team, Thor Waterschei. Waterschei is the coal mine where we are working on. And that was a soccer team that was playing, that was one of the two teams that were merged together to Racing Genk, together with Winterslag, just for your soccer information. And to give you the double meaning of Thor. We have now in that ecosystem, we are a regulatory sandbox, so we can have a number of regulations which are not applied to the Thor site, and we can do experiments which we cannot do in the real outside world. For instance, we have connected, and it's not to, you have the RGAE, the RAE, so the technical code. In the technical code, you cannot use DC for connections. Yes, we connected EnergyVille 1 and EnergyVille 2 along the street, across the street with a DC connection, just to give you a flavor of those things that you can experiment with. So have a look on what we're researching on. We have the thermal electric research, and we're starting from batteries and power transistors and PV, materials for it. You go further up, and then you go to the cells, the module technique with battery cells, storage, integrated component, and heat exchangers. For us, storage is not only electrical, but also heat, and also in next steps, also in molecules. You see here, there are two colors. You have dark green and light green. The dark stands for, looks for thermal applications. The green, light green stands for electrical applications. And then to subsystems, you go to power electronic converters, smart thermal storage. One of the companies coming out of EnergyVille is Thermovolt, for instance. Smart substation controllers, building technology, building assessment, and then battery management systems, where Serge is also going to be pointing to. And you have also the building integrated PV modules. This is a very important one. We're going to start up a number of startup companies, maybe still this year, probably beginning of next year, on building integrated PV. It's going to be fascinating. We have a number of architects in the research groups also, and architects don't like PV because it's ugly. They want to have it colored, etc., and we're going to make it for them. Then we will go further to the building. You have DC nanogrids, where Johan Driesen is going to entertain you about. Then we go to the building electrical and thermal modeling. So co-modeling of electricity and thermal energy in a building. The home energy management system, for instance, a big collaboration with Nico. Building energy, how also the building can act as an energy storage device, and optimization performance of buildings. And then we go one step up. We go to the district design with optimal integration of renewable energy systems, the thermal electric modeling and network design to prove that you can better optimize in a district than every individual house. And then we go to fault detection and management of electrical grids, but also on thermal grids. Then you have decision support of larger grids and towards HVDC systems. And then the top of the list is energy monitoring and policies with scenario modeling and training and management in interoperability. We have 6 big lines of research, each of them with a minimum of 50 people working on them. If they divide 400 by 6, you see that some of them have more than 50 people, but something 40, 50 is a minimum. And you have solar, storage, and as you can see, heat and electrical. You have power control and conversion. You have building and districts, networks, plural, and strategies and markets. If you look at solar energy, we start from new materials, among them perovskites, the material for the 30s. PV modules and performance optimization. Then you have high efficiency, for instance, double-sided PV. Then converters for getting it into the grid. The design and PV building, reliability and aging, and then the real outdoor testing of the system. Electric storage, the topic that you are going to be diving deep in today, is starting from new materials for batteries, where you have typical materials for dry batteries, but also lithium sulfur. It's another route that we are working on. Then modeling and characterization and testing of batteries, the dry rooms where we are working on. The architectures of the cells, where we can go to pouch cells for new things. New cell concepts and also battery concept, the BMS, and the system integration of BMS. To give you an example of people that are interested in that research on BMS, one of the problems is with leasing companies. What is the the still available value of an electric car? What is the lifetime left of a battery? How can a battery be used as a second life battery? There, the battery management system certainly will have a major thing. And for instance, people that are interested in that is Belfius, is KBC, and that kind of companies. Thermal storage with control and the compact thermal storage, integrated storage concepts will be on site. Then power electronic and converter with new materials, gallium nitride, then the magnetic components and reliable converters, but also converters for heat recuperation, low temperature power generation, and heat pump flexibility that then can be used in electrical systems. Building and districts, we are looking at the individual building, but also on district energy performance. We are looking at the home energy management of the individual home, but also how to work on that with the new tariffs that are coming along, certainly in Flanders. And then we're looking at the building technology assessment, where we have done major work for Europe. HVDC grids, where we do the big grids and the interoperability and decision-making support. We have hardware in the loop, RTDS system available. If you have people that like to use it, we will certainly can look how we could accommodate that. And then we have the DC nanogrids. So DC is attacking AC from the top and the bottom. The good old revenge of Edison to Tesla. Thermal networks with control systems, distributed control systems, network design, and the analytics of substations, for instance, and their efficiency. Strategies and market, with the energy market design, we are doing tariff designs, etc., interoperability, flexibility trading, and long-term energy planning. And also we go to energy policy input. I hope you are really have seen that we have a broad the broad system, and I see some questions. But I hope that really you can see that is an open lab. We are there to serve society, and serving society for us means far more than the local society. So we would like to work together. We are looking for collaboration. We offer what we know, but we want to learn from everyone who is part of the system. We will need brains to do this. And I see a question to what kind of thermal energy is linked to the PV is a question of Renaud Dachouf. We are now working with Aztec on a mirror type of application for PV, and that will be linked to the thermal grid, and that's where we're going to have the first link between them. We are also going to work on tandem cells, where you in the same moment produce electricity and heat with the same surface. So that's the way they are coupled. And if you are linking PV with thermal energy in a house, we have done renovation studies where it is clearly proven that if you isolate a house less, but put PV, but still very good isolation, and put PV and a heat pump in the house, the comfort of the house is going up immensely. You have more place, less problems with moisture. At the same time, your energy bill and CO2 output goes to 0 and not to 10% like you do with perfect isolation. So these are two links between PV and thermal energy. And then in Philippe Deguet is asking, in your batteries testing lab, do you have all capabilities required for battery standardization or certification? A certification, I have to ask Jeroen Buscher, but in theory we could, but I'm not sure that we are certified. But Jeroen will certainly be able to warn you on that.
I can quick answer on that. So yeah. we don't do certification of batteries. We are providing performance, aging, all kinds of testing related to the performance and the cycling of batteries, but we cannot perform the destructive testing that is needed for certification. That is something that we don't do.
I've always in my lab always been very hesitating on certification, because if you do certification, your lab has to be very well organized and you cannot do naughty things that you would like to do in research. There's a very delicate balance between standardization and research. Okay, storage is performed by heat and batteries. What about hydrogen? We are working on molecules, hydrogen being one of them. Hydrogen as a storage for electricity will still need an awful lot of time to get enough green electricity to do so. If you now produce hydrogen electrically in Europe, you have the double amount of CO2 than if you would directly produce it from natural gas. If you, Alexis Dutrieux, want to know more about it, send me an email. I will gladly provide you with some papers we have written on that, on those elements. Hydrogen will be a very important thing for industry in the energy system. The energy supply of final use will be extremely limited. But that's, and if so, it certainly will take another 15 years until it would be there. So energy storage also with hydrogen requires an awful lot of space. You need a very more dense energy carrier, and probably you will transfer the hydrogen with CO2 to methanol, which is liquid and therefore less volume. Not going to go into details. Send me an email. I will gladly send you the papers that are dealing with that, which amongst others, Peter Vingeroots have contributed to.
Thank you. I've a global question, because in Europe, especially, we have seen in the last decades that we have tried, for example, to create a solar PV industry, and so a lot of R&D behind it. And we have seen that it was very difficult to provide and to have, in the end, this industry in Europe. What is your opinion about storage? What is the value in the value chain? Where can we put ourselves as Belgian players? Because we know that the competition will be very hard, and it's already very hard. So what's your opinion about the potential industrialization in this topic?
If you talk batteries, I'm not going to give you all the details of the strategy, because not that I'm not want to give them, it would take too long. Our strategy is to go back to the what I showed you. So in the materials, we are going to go to dry lithium ion. And the idea is you can have a better energy density, and you can have a safer battery. Why dry lithium ion? The research we are doing is such that if you, but Philip Peters will come back to that certainly, if you go the route that we are proposing, the manufacturing units that are built now for the present lithium ion wet batteries can be reused. You don't have to adapt them too much. So if there would be battery factories that are going to be invested in the next 1, 2, 3 years, they can easily be transferred to that new, more performant technology. First. Second thing is we are trying new materials like lithium sulfur. So look at those new materials to improve it still further. And then third, for the lithium ion environment, but also for those new ones, look at intelligence in your battery, look at how every cell in your battery can be monitored, so you can have far less maintenance, far more reuse, and far more financially efficient use of your investment on batteries. So 3 routes of work: dry, but don't change the manufacturing environment, new materials, and intelligence. And these are things which are not easy to export, and they are new. Don't try to attract yet another gigafactory. You can also try to attract any other massive production thing. This is not the way to go. And of course, we are collaborating also with setting up collaboration with Umicore on recycling of battery materials. So that's our strategy at EnergyVille, to work on that. And if you want to be part of that, be our guest.
Thank you. Thank you very much. So we are perfectly on time to have the second presentation. So really thank you for this global introduction. It's always a pleasure to listen to you and for your host today. So we will continue this this morning with another presentation from Johan Driessen. He will speak about the storage solution with a focus on power converters, DC grid, and demand response with residential storage. So let the floor to Johan.
Okay. Good morning, everybody. I hope you can all hear me well, and I hope you can see the slides. Let me put them in presentation mode. I am going to present you, as Cedric introduced, quite a multidisciplinary work where lots of technologies are coming together. It is the work of several research teams working in EnergyVille. There are at least 6 professors, almost full-time, behind this work. And now it's my challenge to summarize this only on just a few minutes. Now, first of all, let's start bottom up with the technology. Let's start with the power electronics. The power electronics team in EnergyVille, our vision is that we want to create disruptive power electronic solutions to enable a sustainable energy transition. This goes very far. We are working on converters for high voltage grids, high voltage DC grids. We are working on converters for photovoltaics, but we are also working on bidirectional converters for the charging and discharging of batteries. Now, we have a certain vision about how all of these converters are coming together, and that is what Ronnie has indicated before. We are believing strongly in the return of DC. In HVDC, it's very clear that it has found a place again, but in the low and medium voltage segments, it's still quite experimental technology. And in EnergyVille, we are working on this technology with multidisciplinary teams. We've got people working on the converters, on the protection, on the operation, on the design tools, and so on. And we converted part of the building into a DC grid. I know in Bologna, there's also a quite similar project, the Miracle project. We know the people there very well, and they were invited to our meetings, and we were invited over there already. So there is already some collaboration ongoing on the floor. Now, there are many converters on this picture. We see we need converters to convert solar power, to interface the batteries, to interface the loads, to stabilize, and we also want to make some solid state switches even. Now, behind all of these converters, there is a roadmap that we continuously update. And as this is the work of several professors and their staff, there are many things on this. We work on the level of the materials, on the components, the switches, such as the gallium nitride switches. There are teams in IMEC that develop these. We have people working on the magnetics, the design, but also the realization of the high frequency inductors, for instance. And we've got people working on all of these circuits. There are many classes of circuits. We work on several types, but also several power levels. It goes down from several watts to several hundreds of kilowatts that is being made. And in the back, we have people doing the modeling, design, and simulation of all of this. Now, the circuits that we recently realized were, for instance, for photovoltaics, we've been making isolated and non-isolated circuits where we try to use the gallium nitride converters to show that we can make circuits that are on average 4 times smaller than the classical silicon solutions. For the DC grids, we've been making balancing systems, balancing converters based on silicon carbide. There we need another kind of technology as the current levels, especially if you've got protection problems, go up a lot. And in the end, we are now working on a prototype of a small scale MMC converter so that we can study also the medium voltage types of circuits. On the load side, we go to the totally other spectrum of the power range, where we make extremely small, extremely compact, dense circuits, for instance, to interface small lighting loads, small batteries like charging through USB-C, and so on. These circuits, they have all found a place in a test facility that we have developed, half of what we call our home lab, and I hope to be able to show you on that virtual tour later on a little bit of it. Half of that home lab, that's where we build microgrids. Half of it is AC, the other half is DC, and there we have created a very unique test facility to test all of these technologies and their interfaces. We made it a bipolar grid, so that means we've got a plus, a minus, and a 0. This is the most generic grid, and this is also the grid that allows you to go to the highest power levels, because in the end we've got 1 kilovolt of maximum voltage spread. And this also allows us to host a new standardized voltage, which according to the new proposed international standards will be 375 volts. We have built a system for 100 kilowatt. Currently, we are expanding it again with extra cabling so that we can house a small demonstrator where we show all the typical house loads running on DC, like the kitchen equipment, and on the other hand, the more high power loads for distribution system. The system is also connected to our basement where we can charge a car, and it's connected to the roof so that we can disconnect some of the PV panels and connect them directly through our own converters to the to the system. In this DC grid, we do lots of tests like protection tests, transient stability, but also we can test there several types of converters for batteries and PV systems. I will show you that later. The system is currently also connected to the second building, and that is part of that sandbox regime, the regeluwe zone. So we are, in fact, currently we own the only low voltage public DC line. It's not extremely long, but it's the first one of the country. The idea is to expand this even further in the future. But now back to the storage topic. If you look at storage these days, we see that the storage systems are often proposed in conjunction with photovoltaics. So at home, these converters, then we need to rethink the photovoltaic and battery converters. And also we need to think about how do these converters look like when we are going to the more smarter tariffs with more capacity components, with more flexibility and dynamics in there. So we not only work on the hardware design itself, but we also look at the next level. What are the optimal sizing, placement of these converters in the building, but also if we expand this to an energy community, how are we going to share all of this technology in a small area? Who's going to own the battery, and how are you going to jointly going to use it? Now, if we start from the home, there we see clearly a trend that the classical PV converters that some of us probably have hanging at home, that they will be expanded with a battery unit. There are DC coupled units and there are AC coupled units. as far as we can see, and as far as we can test what is on the market, the DC coupled units, they behave better, and they have the possibility to be expanded to a DC grid. And then we end up again with our vision that DC will play a much bigger role in the buildings. I think also of the charging of the new electric vehicles. Now, of course, we need to address this scientifically. So there are people working on the optimization models, the design models, so that we can find out what is the optimal sizing of the battery packs that you need to put in buildings with PV, what is the optimal interface dimensioning, and given certain tariff structures or other business models, how do you achieve the fastest payback or the best profit out of this system. So here we link also the energy economics with the hardware sizing. As mentioned by Ronnie before, we try to test this all in practice. So we have many of these systems in the lab. Fortunately, you cannot have a look at it, but please come over later. We are testing all of these systems in practice. We have got the facilities to do very low powers all the way up to high powers. It's no problem to have a few hundred kilowatts of testing. We even have a high voltage test facility that is one of the unique ones currently in the country. And we can do a lot of solar related testing with our test tracks and several different configurations of photovoltaic panels that we have on the two buildings for the moment. Okay, now, secondly, I wanted to present you a little bit about the control aspects, and that's mainly my colleague here, de Koning, who's excused, who is supervising that, because you can always optimize the hardware, but in the end, somebody's got to find out what you will do with that hardware on the operational side. And there we look a lot at distributed control and the optimized use of the distributed storage assets. Now here's de Koning and his researchers. They have, for instance, been looking at the value of the storage, especially considering that you can use these storage systems for several energy-related services. What I, for instance, mentioned before in the frame of the PV systems, that is self-consumption, maybe a little bit of PV, a little bit of peak shaving. But if you go on the ancillary services market, you can also try to value or monetize your battery by offering frequency containment services, frequency restoration services, and so on. The good old primary, secondary, and maybe tertiary level of reserves. But the challenge is, how do you combine all of these services on the same type of assets? Geert has been looking at this together with Jonas and Bert. For high power batteries, large batteries. For instance, this is a result where they looked at the different control scenarios for a Tesla type battery, so a large outdoor battery. It's actually an existing system in the province of Limburg, and they have been looking at how to optimally use this. This involves a lot of stochastic optimization, and also not just how to make most money out of it, but also how to how shall I express this, how to gently use these assets so that you don't wear them out too quickly. So things like degradation of the assets were taken into account. We did not only look at this problem for the large centralized battery, it was also studied for fully distributed batteries located in several houses. So the problem was expanded then to a large-scale distributed control problem and the related stochastic optimization. And there he could show that you can make a good balance by still implementing that self-consumption goals, which is good for the energy bill with a large peak component, but at the same time the spare capacity can be used to offer reserves. Of course, this is for the moment still, these things are still in simulation, but we are doing the first tests with some reference systems in our labs as we speak, to show that these things also work in reality. Now, looking at the time, I'm going to conclude here. So to conclude the part of distributed control and optimization, this is of course more something that you do on the computer. You need lots of data, good models, but there we complement the work with the people working in the lab and working with the hardware testing very well. We've got data scientists and power electronics specialists who all work in the same teams and learn from each other. We've got the people doing this optimization. We've got the people doing the designs of all the hardware that is needed. So in the end, we can cover the whole value chain from the battery itself all the way to the application, also in EnergyVille. Thank you very much.
Thank you, Johan. I don't see right now a question. I will ask the first one. So for the others, don't hesitate to ask through the chat or raise your hand. I have a question. You have mentioned the DC nanogrid. For the buildings, it's more and more a hot topic. We can suppose that we can integrate all the DC components directly inside the building materials. And so for you, what is the main challenges over there? Because we see there is a potential, but still, if we put some DCs everywhere, right now the project that we have in DC, it's more industrial based project. So what are the main challenges in this area? At the market view, it's a mix of technological, but as well at security and market.
Yeah, I agree. I know the Miracle project very well. Indeed, it looks more at an industrial feeder. Now we focus more on maybe a smaller scale of DC application, but I think the challenges are very common. The challenges are first of all found in protection and safety. A lot of people, if they hear DC, they still get an allergic reaction because they learn in school that AC is the only safe solution. But I'm not saying that AC is safer. I'm just saying safety is different. We have shown that you can also do things like residual current detection, fault interruption, but just the characteristics of all the faults are different, and we are just learning by doing. And there we have a bit a chicken and egg problem. In AC systems, they have got 100 years of experience. Here we are working with technology that is developing, and at the same time, there are no clear regulations yet. So, for instance, in one of our projects, we are working on one of the Flux 50 cluster projects. We are working on the technologies that are needed, but at the same time, we are writing a kind of grid code that could be used as a sort of reference text for maybe upgrading the array degree. That is the national safety code with the needed chapters on DC. And at the same time, we also participate in some of the international standardization activities. So Ronnie indicated before, it's not always the natural habitat for scientists to be there, but in this case, we need to be there because I think in this international standardization, a little bit different from what you see elsewhere, the scientists are taking the lead with setting the new voltage standards so that we are not going to make the same mistakes again like in AC, where every country had a different socket and a different kind of voltage rating in the beginning. Here we go for a global technology right away. So the challenges are you have to do this multidisciplinarity or you don't do it.
Thank you. I've seen that there is a question in the chat. So it's a question from C+T and that grid. they have a project in DC in Wallonia. So, so the question is, what is the advantage of having a bipolar connection with around 375 volts compared to unipolar?
Yeah.
700.
Okay. Yeah, there are several advantages, also disadvantages. I don't hide that. One of the advantages is that the losses are lower. You can spread your currents better, you can balance them better, you can connect high power and low power loads in an easier way, because in a bipolar system you have 3 wires. You can actually see this as a disadvantage as well. But since you have 0 wire there, you can have a little bit of unbalance to connect when you connect the smaller loads in a unipolar way and the bigger loads in a bipolar way. At the same time, this also gives you a little bit of redundancy. If, for instance, there is a problem with one of the wires, you can continue as a unipolar system. And that is something that is favored in UPS systems. But I think in practice, these systems will coexist. It's a bit similar to AC systems, where you have 3-phase systems next to single-phase systems. The equivalent is bipolar and unipolar. Now, one of the disadvantages next to the extra wire that you usually install is all the protection questions are a little bit more complicated in bipolar, but that is something that scientists, of course, love to solve.
Thanks. Another question from Denis from Genkois. He's working in the recycling of the batteries. And his question is talking about revenue stacking, how the facturation is done. So we may have some revenues from the energy supplier, Elia, or the local network manager, or a cooperative, or energy community.
Well, let's say it's a good question. For the moment, I have to mention is you cannot legally implement all of these ideas that we have looked at. We just wanted to show that there is potential, that you can handle this, that you can use the storage assets much better without causing too much degradation. Now in practice, especially in Flanders, the tariffs and all the invoicing is going to change a little bit. But here, a lot of these incomes are generated through an external party, usually a kind of aggregator. Actually, part of that research was conducted with one of the aggregators who's active in the Flanders region. So they take care of a lot of these services, and then they have agreements with the people that offer the assets to them to compensate them for the use.
Okay, thank you. I have some question in the private part, so I will read it. So is DC an important step for the transport to make it electrical transport? So for you, it's the next phase, or?
Yeah, well, from the beginning, electric mobility always had the DC inside. There was no reason to have AC on board of a vehicle. What we see there as a trend that is that in all the electric vehicles, also with the size of the vehicles growing, we are now looking also at the trucks, for instance. The DC voltage buses are growing in voltage. 800 volt is a new standard voltage for electromobility. Also, the charging needs to go at a higher power. Now, in practice, we started with charging our cars in the more standard sockets. You can push that a little bit, but there's a maximum power of something between 40 and 50 kilowatt that you can realize in practice. The moment you go above 60 kilowatt, and currently the new fast charging standard is 250 to 350 kilowatt for cars. You can only do that with DC in practice, with special plugs, the combined the CCS combined plugs, new types of chargers with even with internal water cooling of the cables and the plugs, but that is the new way to go. These fast chargers, they will gradually replace the traditional additional fuel stations along the highways and so on. And you see the same trend, by the way, also in, for instance, public transport in Flanders as well as in Wallonia. The LAN and the TEC, they are currently all doing pilots with electrical buses. Now, some of these pilots, they have charging powers of, I think 500 kilowatts for the moment, with overhead chargers, flash chargers, extremely spectacular, but it's all in DC because of that power level.
Yes, you're right. We have bad experience with our buses electrical right now. So
yeah, we have a learning curve.
So as you know, we have a project that is starting is between the AC and DC and conversion inside a microgrid for really a microgrid in for between SMEs. What is your point of view about the gain, the final efficiency of the system? Can we have a percentage that you have in mind that we can have when we put all the system in DC? So when we change solar batteries and so on, and what is the global gain that we can achieve?
Okay, well, we mainly looked at this for big buildings. The case of of a longer distribution feed is something that we're still working on that. But for bigger buildings, which is I think comparable, honestly, on the efficiency side, it's not very spectacular. Yeah, you win a few percent, of course, of losses because you basically eliminate complementary AC/DC conversion, so it's not more than logical. But honestly, these converters were not bad at all. So okay, you have a few percent losses that you save, great, but that doesn't pay for the change. We see the biggest financial advantage in practice is on the investments on the capex side, where if you design these systems correctly, you have a lighter type of cabling, you need less power electronic converters, and for the models, well, for the designs that we made, we ended up with having up to 30% of cheaper systems. So it's mainly on the investment side, and on top of that, that's something that's hard to quantify because it depends on the application. There's also an increase in reliability because in DC with your batteries throughout, you're basically living in a big UPS system. If you're, it depends a bit on what you do in the building, but in some buildings, this has a very high value, this reliability. So there's another type of saving then.
Yeah. Thank you. And last question that I've received, it's about lifetime. So we have seen that there is a lot of application that we see right now. The first two that have a market is the frequency central services, as you have well presented. It's big batteries that we can see over there. The Tesla, for example, the big projects that are coming in Belgium. And the other is the storage for self-consumption, let's say, and the peak. But what about the lifetime of this type of storage? Because we've seen in the past that it's always tricky. And when with your experience, let's say, you say that you are disappointed by with the lifetime of the batteries.
Well, not really. Maybe I formulated that wrongly. Honestly, we are rather surprised by the lifetime. Some of the experiments that we are doing, if we look at the remaining capacity after we have been doing a test with them in the lab, it's always better than it was anticipated. We also see that with the electrical cars, and that's why we also believe in things like second life batteries. They clearly seem to be having a place. But I have to say, if it comes to lifetime, we work more on the interfaces, and there it's power electronics and reliability is a topic on its own. It's also relevant for solar. We know how to tweak the designs a little bit to take out the components that fail or add extra sensors. So we can now these days make circuits that will live normally as long as the solar panels themselves. With the batteries, it's anticipated anticipated that they will not yet live as long as solar panels, but that day will come. I'm pretty convinced of that. But there, I think later on we will, other people will present more at the batteries itself, but we have people from the University of Hasselt with whom we collaborate in EnergyVille. They are making specific models on lifetime prediction and also how to tweak the electrode designs, because you can play a little bit with the rare elements in there to achieve a higher lifetime performance. But that's still an open field to be investigated, but our experience up till now is actually much better than we had anticipated.
Very good news. Thank you, Johan. So we are perfectly on time to make the other presentation. It's Philip Peters. He will present us the battery material research.
Hello, good morning, everybody. Thank you for arranging this webinar, and nice to meet you all in this virtual way. Indeed, I'm going to explore further with you on energy storage materials and what we do in EnergyVille on this topic. Now, to start, I will take one step back and up to a higher level in the sense, you know, we have this global challenge of we're trying to reduce the CO2 emissions, and we need to move this to reusing it. In this graph, we see the CO2 emissions in view of forecasted in time for agriculture, for food, for transport and buildings, and then for the industry, and then the total of it. In the first step, we would like to come to around 2050 to a zero CO2 emission for energy generation, transport and buildings. And how do we plan to do this? Well, we all know we have to reduce, of course, the energy usage itself, move to renewable energy with less CO2 emissions. Energy storage is an important element, and then also energy management to better use our energy vectors. Now, if you want to come to a really total zero emission by, say, later in this century, then an important element will be to do the carbon capturing and utilization. And so important in this whole transition, you see the energy storage is a key element, and then also moving this to this carbon capturing and utilization, which in a sense is also kind of reuse, but also a way of storing the carbon that has been released in the past. Now, in this evolution, it's of course important that all these energy vectors will continue to or start to work together more than they are now. Generation, the energy management part, the renewable energy, but also here the different energy storage elements, short-term, long-term storage, and this conversion into new fuels generated in this way. So storage is a key element, as you are aware of. But before moving into storage, I want to just draw your attention, because not all of you may be aware of it, that solar photovoltaics has become the cheapest source of energy. And this graph gives on the one hand levelized cost of electricity, which is globally depicted here as a formula, for different types of energy generation. On the right hand side, you see nuclear, coal, and gas turbines. And on the left side here, different types of solar. And we see that the utility scale solar, so the big solar plants, even in our region in Europe, have the lowest cost of levelized cost of electricity compared to all the other sources. Commercial PV, like on big roofs, on warehouses and bigger installations, but not full utility related, have a similar price level. And of course, residential, because of the smaller scales, is still a bit higher, but also there the prices are going down. So this means PV is there, will be there, and we have to take care that we can connect it to integrate and take care of the intermittence, similar as we have also like with wind, for example. And so an element that is important in this is the storage. Further integration of PV becomes very important, because next to PV plants, we will have it in residential, we'll have it also in buildings, and Ronnie Belmans in the beginning already mentioned that this is an important development that we're working on in EnergyVille. So PV in that sense becomes a building component where cost is a challenge, and also the flexible customization. And that is something that we're working on together with partners also in Wallonia, Typically, these building integrated PVs are quite a manual way of working because you have to adapt all the different modules to different sizes, fitting the whole building and the different parts of the building, which all may have different dimensions. And if you have to do this in a manual way, it's quite expensive. But we're moving into a solution where you can do this in a scalable, custom automated way, enabling also for sure lower cost in a fully automated industry 4.0 concept. We have a tool at our EnergyVille labs, which unfortunately you cannot visit, that allow us to do so. And we, through pick and placing, we can actually interconnect them in a clever way with a new material and a new interconnection style. We can actually interconnect these PV panels and having different dimensions, different sizes automatically assembled, which allows us to bring down the cost of this type of fancy buildings. We don't do this purely on the module level itself, but also integrating them into the building components together with our colleagues at the KU Leuven. And you might, of course, recognize these buildings here in Liège. So this is an important element of our work in EnergyVille as well. But of course, as mentioned, PV is a key element in renewable energy next to wind and other sources. And this brings us then also, well, how do you combine this with storage? Because PV generation is mostly during the daytime, of course. And we have energy users also at night and the evening and the morning. And we need to shift the generation peak of PV into these other moments during the day, and batteries are crucial for that. And Johan Andriessen already showed some scenarios to manage this actually shifting of the loads and shifting of the generation of PV into this other moments during the day. Now, if we dig further into new battery concepts that are possible, well, you have to see there's a whole spectrum of battery applications and use. You have the smaller capacity of smaller power batteries and the higher capacity batteries. And with our technologies that we develop in EnergyVille, we can span the whole range. We have on the one hand the development of small, what we call micro batteries, that existing of a thin layer of a 3D structure. That can be used for power in the package for all kinds of small and novel applications, as I will explain further. But what it is more importantly for the topic of today is, of course, this large capacity storage for grid, for automotive, for energy storage at larger capacities. And this is then important to also link this with smarter cells, smarter batteries. Now, how does our new solid state battery concept work? On the left-hand side, you see here a more traditional wet type batteries with current collectors, different particles, and separator, which is separating the both polarities and both elements at both sides of the current collectors, an anode, and also on the other side. And then we move this into what we call this new solid state battery, which we want to make more safe by using this solid state electrolyte. So the electrolyte itself is a solidified component, as we will explain. We can have more energy in the same volume because we have a more dense packing by using of nanoparticles. We can even have faster charging, although the electrolyte is the solid component because of the high ion conductivity that we have in this solid electrolyte. And we can have a longer lifetime because we have protective coatings that we apply onto these particles or this mesh porous structure, which allows us to guide ions and actually have less stress in between the different components. So these are the basic elements of our new solid state batteries. And what do we want to achieve with this? If we see the energy density evolution in watt-hours per liter in the view of time, we see that these traditional wet ion, lithium-ion batteries are actually coming to a limit. And it's not only us who say that this is shown by the nature of this type of wet lithium-ion batteries, that they come to a limit around 800 watt-hours per liter. And if we want to go above that or break this limit, we need to move to these other materials. And these solid state batteries are expected to be the technology to overcome this. At the IMEC, as partner in EnergyVille, we have been working on this since a couple of years, and we are moving along this target here to come to 1,000 watt-hours per liter in the coming years. We are currently around 400 watt-hours per liter recharging in 2 hours. And so we have in our roadmap this 1,000 hours per liter in the near future. And this is enabled by this solid electrolyte, a solid composite electrolyte. And although it's a solid material, it has an higher conductivity at room temperature of about 10 millisiemens per centimeter, which is actually already better or well, similar and slightly better than actually the ion conductivity of wet batteries. And this is because we have, we call, it's kind of a solid liquidified material that we use. Another structure is also an important element is this 3D nanomesh structure, which is actually a very dense mesh with a high surface area that is then coated with this electrolyte, and in this way gives you a very high surface and a high dense material that gives us this high electron density of this high energy density. And we use this for the cathode and then with lithium metal on the anode. Now I have here a movie that shows the concept of the batteries that we are developing, and I will try to run this. I hope the sound will come through, and if not, please let me know. I hope you hear the sound.
No, not yet.
No? Okay. Then I need to switch. Just a second. Just a moment. Let me switch here to the system audio.
Sound is better now?
Not yet.
Or maybe you can speak, just presenting the video. I don't know.
Yeah, well, I thought I switched the sound. I thought it was working because I hear it myself, but okay. Yeah, so we have the liquid precursor that is coating the films. And this makes that it's compatible with current battery manufacturing because also their wet electrolytes are used, and we use it here also. We impregnate the film with this wet electrolyte, and then it solidifies. And by the solidification, you make an intense contact between the different particles, allowing you to have this very dense and intimate contact between the different materials. And so we have this whole pores, and these pores act while coated with this electrolyte as highways for ions, which go from the one electrode to the other. And we don't need a separator because actually there's a little bit extra of this solid material which forms actually the barrier between the different materials, the separating itself. Now you can actually check the video yourself again. Let me just switch here then.
On this link here, which we share the presentation. So on this link, you can review the video itself with the sound. So my apologies that it doesn't work, but you can see it. Try to show you that it's by applying this electrolyte in, first of all, in a wet form on equipment that is similar as currently used in battery developments. There is a solidification step, and then you in the end up with a solid material, which is in that sense non-flammable anymore because all the solvents are out. So in that sense safer, and it has a very high ion conductivity, allowing you this fast charging and good battery performance. So if you then compare with the different batteries that are out there, this is again this energy density on the left side. Let me put my place point. Energy density on the left side, and then the charging rates Of course, with very thin films, you have very fast charging, but very low energy density. And then you have other material concepts which can give you bit slower charging but higher energy density. And the typical batteries used, like for cars at this moment, have this type of NMC type of material composition, which have charging, say, in about 1 hour or a bit less, a bit more, depending on the type, with this up to this limit of 7 watt-hours per liter. Currently, with the solid-state batteries, we are here at this 400 watt-hours per liter at a little bit less than 1 hour charging. And we're moving into this direction here to really cross this boundary and being applicable for example, automotive and other types of storage and fast charging. Now, where do we do this research? In our labs in EnergyVille, we have extensive equipment for that. We have to process the materials a big dry room where we can make prototypes up to these pouch cells. So to really test the materials in like they would be in a real battery. Of course, the materials development themselves and the upscaling, we have various set of equipment to do this. And Serge in the next presentation will also explain we have a battery testing lab where the batteries we develop here can be further tested. Now, in next step into after really the battery development itself, we see a future for more smarter batteries. And in this way, we can further increase the quality, reliability, and lifetime. So making batteries more smarter by adding, on the one hand, a closer link to the controller, as Sergio will explain, but also integrate sensors into the batteries and the different elements themselves. It could be thin film electronics that could be used there, which is a development we do at IMEC, where we have processors and different sensors can be made on tin foils. And we have also, of course, all the electrochemistry technologies I've shown you already a bit about that can be used for that. And with these smarter batteries, with sensors integrated, we can develop an improved BMS system, as will further be explained, which have increased energy available, increasing charging rate, lower cost and packaging can be done, and can in the end be safer to control and to manage. And also towards second life sorting, there is a benefit for that if you know what has happened to the battery. Now, apart from the large-scale batteries, as explained in the previous slides, we also work on what we call micro batteries. And micro batteries, we have a lot of material development that is going there, and important is also the interface layers. Now, if you want to make small batteries, of course, you can make the small thin films, but if you have these thin films, they can charge very quickly, but they don't have a lot of volume, so to say, to have a lot of energy stored in it. By making these 3D shapes and covering them with those battery materials, we can actually still have the combination of very thin layers which allow fast charging, and in the end a big volume of material that allows you considerable size in energy storage. And we see specific application domains for this, which are like medical implants, flexible thin batteries for all kinds of IoT and miniature applications. We are, for example, working here on the digital lens where there was this type of battery that can be integrated and so on. So this is a specific market for this type of micro storage that we are targeting. So this brings me to the end of this first part, which is battery related, which is more for the kind of you could call shorter term storage, which is essential, for example, in the day-to-day storage for electrical vehicles and so on. But if you want to look further ahead, there is certainly need to do more, to have longer term storage. And if we can combine this also with using the carbon from the environment to transfer and to utilize into this new kind of renewable energy fuels, that of course is an excellent advantage. And electrolysis is a key technology block for that. And from there, we can actually use renewable energy from wind, from solar, and transform this into these new energy sources, hydrogen and other carbon-based chemicals for the industry, for mobility, and for consumers. The key element is the electrolyzers, as mentioned. I won't go into detail. I think from our chemistry and electrochemistry courses, we all are quite aware on how this works. Now, the question is, of course, how you bring this into practice. The electrolyzer nowadays, of course, exists, but it's very bulky system if you look at these big electrolyzers for hydrogen production. But the key element is this electrode membrane assembly with 2 electrodes and a membrane in between. And that is the focus of our development to bring this technology to a next level. Here you see the traditional membrane assembly as, well, is currently used schematically, where you have an anode and a cathode. We have here the ion exchange membrane in between, and you have flow plates on both sides, which are sealed. Now, what we want to do is make this much smaller in the sense that using a nanomesh technology, as I will briefly explain in the following slides, which is embedded here, making a much thinner electrode assembly, membrane electrode assembly, which allows you to have a higher energy density. By using a nanomesh structure here, which I will explain, gives you a higher effective surface that is possible. With this bigger surface, with high porosity, you can actually have a high throughput. There is an intense contact between the different elements, which gives you a reduction of the ohmic losses. And by using nano materials and with specific nano materials for the catalyst, we can have improved kinetics. And then also we reduce the number of precious materials that is used. In principle, there are no precious materials used. And we can lower the cost of the whole system. So this is what we're working towards. And as mentioned, the key element is this nanomesh structure, where you see a schematic here. It's a kind of the same structure as used for batteries, but then activated in another way. Typically, what you have is this in existing nanomesh structures is this type of thick foam, which has a high porous structure. But we, as mentioned, use this microstructure, thin nanomesh, which is very much very smaller, has actually a very high surface area for the same porosity, and it's a very regular structure, and it can be made very thin. Actually, you can make it bendable even if needed. It's freestanding and it's flexible. Now, here is also different schematics. The nickel foam, platinum, copper, carbon cloth is also sometimes used. We developed this nanomesh structure here, which can be very thin for a similar porosity. And you see these different materials also really producing this hydrogen in this set of examples, where you have the nickel foam, the platinum carbon cloth, which bubbles a little bit. Our nanomesh structure is bubbling heavily, showing that really hydrogen is produced in this example. So, but this is the current step, is that we are developing this membrane electrode assembly using that nanostructure, being the core of the electrolysis system that can be used with renewable energy as source, producing hydrogen. And hydrogen is the first step. And as Ronnie already explained, it's not the ideal material to really use as energy storage, as energy density. But of course, it can be used in the industry. It could be used in fuel cells. But in the next step, we want to combine this with carbon capturing and actually combine the carbon with the hydrogen into new carbon-based chemicals that can be used, of course, in the chemical industry, but also to be stored and to, in this way, have a longer-term storage capability. And that brings me to the end of this presentation, where I mentioned that there is more renewable energies there, certainly PV and wind. And this involves that there is more need for storage. On the one hand, we work on batteries, focus on the material itself, the solid state materials and the battery concepts related to that, giving us higher energy density, faster charging, and also safer batteries because they're not flammable anymore. And then we make the link to hydrogen, or what we could call power to molecules, where we further optimize the electrolysis process using our nanomesh structure, making everything more compact, smaller, and in that sense also lower cost. And this is done in a scalable process using atmospheric chemistry. And then the hydrogen is the first step. And this is the intention then to be further combined in the next step with the carbon from the environment into carbon capturing and utilization. Voila, this ends my presentation.
Thank you.
If there are questions.
Yeah, there is some question because we have material experts in the room.
Yeah, well,
we're quite happy to make the link with the first question is Philippe Deget from University of Namur. Dear Philippe, are you already studying battery generation beyond next lithium-ion batteries? Which type of more available and less scarcity metals mixture do you think might be interesting to investigate?
Well, there are in our group at University of Hasselt and IMOMEC, there are developments ongoing on other battery materials. Lithium sulfur is, of course, and one that everybody looks about, but there we see some challenges with the reliability, the stability of the material. And then also lithium air is one that is being explored further, and also lithium. There's different types of materials. So indeed, but I have to be honest, I'm not a material expert in this, so I can couple you back to the different people involved in this research, giving you much more details of what we do in this field.
Okay, perfect. Do you also use the question from Nathalie Job from University of Liège? Do you also use the nanomesh for fuel cell electrodes?
Not at this moment, but it could be. It's in our roadmap to, if there is the possibility, well, we have limited resources, so we have to choose. But it's in our roadmap if there would be interest and if we would have the capability to also use this for fuel cells. Yes. But as mentioned already, hydrogen is not the ideal energy vector in that sense. So maybe it has more added value to use together with carbon to get more higher value energy bearing chemicals than pure hydrogen. But in principle, we could work on hydrogen if there would be the interest, and then fuel cells, which is just the reverse in the end.
All right, a question more general from Baptiste Dutron from WeSmart. How do you expect the price of solar panels and batteries to evolve in the future as more energy will be produced by renewables, increasing its uncertainty to intermittence? It's more a global question about the prices that you can feel.
Well, prices will of course go down, similar as the price for solar cells has gone down the past years due to the fact that more and more are produced. There's more learning on this. This will be the same for batteries. We see the price already has decreased since the last couple of years, and it will continue to do that. So in the end, if you kind of make the same analogy of solar cells, the cost of batteries in the future will become so low that it will not be determining anymore, and more the services that you can get from using the batteries and the energy flows in general will become more and more important.
All right, I have received another question privately. So we have seen in Flanders, there is a company, Green Rock, that is coming with a solution, the salt water battery solution. So what's your opinion about this technology? There is a roadmap that you have for this technology?
To be honest, not that I know. I don't, as far as I know, we don't work on this salt water batteries. So I'm not familiar with this type. So again, I can refer you to our battery material specialist who, give you further information on that.
And maybe a last question for myself. I see. So you are working for the synthetic fuels because with CO2 and H2 we can create, of course, synthetic fuels. Have you been surprised by the decision of the airplane industry more to focus it on hydrogen to fuel the planes in the future and not to use as synthetic fuels? Because as an engineer, we can feel that the best solution is maybe to use a synthetic fuel for this type of industry. And as you know, this industry is very important for Wallonia. And so it's a very important question for us, because there is two paths to use for the future: hydrogen as direct vector for the planes, or the synthetic fuel. Do you have any clue or?
Well, I think both are possible, but I have to be honest, I have been in discussions with a big Middle East airline company myself the past months, and they are looking into synthetic fuels, not necessarily hydrogen as such. So they see the need of moving to a more ecological way of flying. Certainly with the current situation in climate change and actually the bad kind of advertising that they get, and people don't want to fly because of they're polluting too much, and they're heavily looking into moving into synthetic fuels there to, first of all, to complement part of the fuel they're using, and ideally to move fully into synthetic fuels. And in that sense, I think well, hydrogen is of course now already available from sources that are coming from renewable. Synthetic fuels, that's still a longer way to go, so maybe there will be a tradition in that. But maybe Ronnie can explain some more. I see him waving his hand.
Yeah, I can explain quite easily. I'm just sending, because he asked for it, to on the question on that respect, from Alexis Dutrieux. I will send him a paper on that. I will send it, Cedric, also to you, so you can distribute it further on. The answer is quite easy. There is no space on an airplane to store hydrogen. Okay, hydrogen is a lousy energy carrier volume-wise. You will certainly not use liquid hydrogen on a plane by minus 253 degrees. And if you want to compress it, you have to carry so much steel that the plane doesn't get off the ground anymore. So you need liquid fuel, period. And the only liquid fuel which is reasonably there at room temperature, the easiest one, is methanol, which is a combination of hydrogen and CO2, which requires, again, so it's the most easy syn fuel. It may, we may have other syn fuels, but for flying it will be a syn fuel. I will share also the papers with you. Feel free to distribute them. It's a paper that we have written for the Florida School of Regulation, where there is the basics of hydrogen will be massively around as a basis for chemical industry and as a basis for syn fuels. You will not see almost any hydrogen in final use for heating, driving, or anything like that. There it has too lousy physical physical characteristics to be stored, to be there. For instance, if you would if you're going to import solar energy via molecules from Saudi Arabia or Morocco, and you would try to do that here, you need a strategic reserve, as we do with petroleum. And if you would need to store 3 months of strategic fuel via hydrogen, yeah, Belgium is full. And you can store 3 months of petroleum in Antwerp on a few hectares. So the liquid fuel is something you need. So there is no silver bullet, and thank you, Philip, for giving me the floor on this. But I will share it, as I said, with Alexis, and I will send you the same mail. So feel free to distribute it among your members. It's a very interesting debate, and that's why we also go, as Philip clearly said, the whole way, making hydrogen for fun, but making those other molecules as a lot more added value, and having them on the same substrate as PV and having that combination that will certainly help per square meter to produce whatever things that we need for the energy transition.
Okay, perfect. Thank you
Thank you,
for both of you for the presentation, a very interesting presentation, and for the comments afterwards. So we still are on time, so perfect. So thank you for all the speakers. We have now Serge Peters, so that will speak about the battery management system. Serge, the floor is yours.
Let me share the presentation. So share my screen. And I need to enter the presentation mode. There we go. Come on. Yeah, that should work. I hope that everybody's seeing my presentation.
We've seen it, but it's not the full page.
Ooh, okay.
We see it as you see it as a display. So we see the next slide as well.
Yeah, Serge, you should switch to presenter mode.
Presenter mode. Okay, I will do it another way. That should work too.
Yes.
Okay, great. So we have been talking about material. So as Cedric mentioned, I'm Serge Peters. I'm a business development manager for activities related to the electrical storage systems. We put the slides together with Jeroen Buscher, who is a product manager for the electrical storage systems at EnergyVille, and we are both working for Vito. Just maybe to show, to let's say reframe a bit the situation about how we are contributing together on the electrical storage part. So I think that it's obvious to have in a circular economy model to have it in a circle shaped about the different aspects. So on the active material side and the battery cells, yeah, it's clear the University of Hasselt and IMEC are playing their significant role. KU Leuven is more on the integration side base, so that we cover indeed the cells and the power electronics and all the equipment that is coming along. And Vito is combining actually the different elements into the systems. Just a few words about the fact that at Vito we have also activities related to material developments related to batteries. It's our math department that is dealing with that, but it's limited activities for the time being on batteries. And we are investigating how to contribute together with IMEC and University of Hasselt. Okay. Batteries, we have indeed a vision about the batteries because batteries are enablers in the acceleration to the shift towards sustainable and smart mobility, but also supplying clean, affordable and secure energy services. And it should be also integrated together with the clean and circular economy and the directives indeed of the European Commission. So today, the battery market is mainly dominated by the lithium technologies. And the price drop that we talked about earlier is indeed a real effect that we have to take into account. And there are competitions with other chemistries. We talked about the solid state, but there are also ion-based derivatives like a sodium ion, sulfur ion, and other chemistries that are coming along, and that can be probably also interesting on the long term against the existing current technologies. Further on, there is more and more attention that needs to be put on the aspects related to reliability, safety, costs, and the lifetime of the batteries. And there are new directives where we are, as EnergyVille, also contributing on, related to the second life viability and feasibility of batteries, and sustainability and intelligence within the battery as well. Think about the fact, for instance, related to the intelligence of batteries, that actually when a battery is leaving the factory in China, coming to Europe to be integrated into the electric car, that actually the quantity of energy which is stored in these battery cells is by far sufficient to move it to the end location for the assembly. Okay, so talking about batteries more from the system perspective. And the first thing that I want indeed to highlight is the safety element. This is a picture illustrating what happens to my colleague in the winter last year, related to degradation of a battery, generating a lot of smoke, fire alert in the hotel in South Africa. And imagine that it could actually be worse than just smelting the plastic around it. And if you multiply that by a factor of 1,500 cells, it looks much more uglier in terms of the results related to the safety. And imagine that you multiply that by 20,000 into a battery container. What can happen? So safety is a critical aspect to operate lithium-ion batteries. But it's more than just safety alone within the batteries. Think about the electric mobilities in cars. So you want to have some certainties in the radius. So you want to maximize the range so that you can still, let's say, move yourself with the same, let's say, perception than you were doing with the traditional engine and combustion engine cars. But it's also related to, yeah, we can't wait that long to charge the car, so it needs to integrate also fast charging. It's still on these let's say additional aspects related to storage. When we look into the stationary equipment, there is a higher share on renewable energy and, of course, of intermittency that needs to be absorbed. But it's only true to implement it if you can increase the revenue that it's generated by the storage capabilities. And finally, we want to maximize the lifetime of using the battery. So it's not only the repurposing that is important, but it's also the fact that you can use batteries longer also in the first application area. So therefore, we need some addition and add electronics on top of that, which is called battery management systems. So at Vito, we developed BatSense, which is a battery management platform, a concept that can actually serve all different stakeholders in the battery business. We concentrate the BMS development related to sensing, high voltage control, on the protection, of course, for the safety elements. It delivers a lot of information related to diagnostics. It's also interfacing to the outside world and to the energy management system. And it allows, in fact, to better perform in terms of capabilities of the batteries. So with the BatSense platform, the purpose is that we implement the solution that you need. And it's not specifically always aligned with what the customer are asking. And this is what we are going to illustrate over here. So the BatSense platform is a modular master-slave design configuration. And it's flexible in hardware and software. You see at the left-hand side that we have two different approaches in terms of potential slave units hardware implementation. The technology is based on or the platform is based on patented technology and algorithm that we developed within the frame of the EnergyVille collaboration. And we are not only monitoring the traditional parameters of the batteries, but we are also providing with the battery management system the key elements for the energy efficiency of your system. So the state of charge, state of health, and state of function is part of the offered platform elements. The development is based on battery expertise. So since 9 years now, we have a battery test lab. And on March next year, we will probably be the biggest battery test lab in Belgium related to battery testing capacity. Maybe to fall back on one of the questions that was raised regarding to the certification of batteries, we work almost like an accredited test lab. So we can guarantee the results. We calibrate our equipment every year, and we deliver a copy of the certification process related to the calibration. But what we don't do is work into the accreditation framework, which is very expensive and with a lot of constraints that Ronnie mentioned that we are not really interested in when we are in the research trajectory. We are working on multiple chemistries and a lot of different application support, and we will illustrate that. We have references. And it's also important to mention that it works on hybrid storage. So if you think about the combination of lithium-ion batteries together with supercapacitors, this is something that the BatSense platform can support. And finally, we are following and guiding regulations. So you will see also at the end of the presentation links to the standards, to the battery EU standards that are applicable for all battery systems in Europe. And the product is dedicated for the battery cell integrators, BMS, and energy management systems developers for the integration. The first reference that I want to talk about is it's a stationary application. This is the 250 kilowatt-hour battery system working on the microgrid integration in the frame of the Découvrez project in Flanders. It's a local community for energy. And the second reference is indeed illustrating the electric mobility, not on the road, but on the water. And this is a leisure catamaran boat, which is fully electrical, equipped with the solar panels and also propellers that have both function to allow moving the boat, but also allowing to charge the batteries when the boat is running on wind. Better performance and promising actually services related to improve the performance. When we consider working with the lithium-ion batteries, there is a safe operating area under consideration. So the batteries cannot operate in very high temperature, but it doesn't work either in the low temperature, far beyond zero. It's difficult in operation. So a conservative way to work with batteries is to have a conservative, safe operating area. When you want to maximize the lifetime of the batteries, there is a preferred operating area. So you reduce actually your boundaries and you can expect to have a maximization in the lifetime of your battery. So working with the batteries longer. To increase the revenue, it's the opposite direction. You would like actually to overrule a bit the conservative safe operating area. And for faster charging as well, you going actually into the limits of the batteries to allow to have a faster charging and faster operation and faster availability. So we need, in fact, to look into a dynamic way of operating. When it's getting cold, you have to reduce that safety operating area to allow, in fact, the battery to operate in a safe way. But when the temperature is increasing, so when there are more favorable climate conditions, the safety operation area can change again. And the last topic that is of importance into the safe operating area is to take into account the aspect related to the effect of the time on the battery as well. So it leads me very easily to the battery degradation aspect. And I'm not a real specialist and not a real chemistry specialist about the degradation on batteries. But there are a lot of aspects that are contributing into the degradation of the batteries. The causes are the time, of course. The more you use, the more that you are actually abusing not abusing, but you are degrading the operation of the batteries. The high and low temperature, the high and low voltages, currents, and other aspects. And you have here a few names of the elements that are seen into the battery. So there are active material dissolution, surface cracking, loss of active material, lithium plating, and all that kind of stuff. But in fact, the result is a capacity fade and a power fade of your batteries. And the question is that how to use a battery to extend its lifetime without sacrificing the performance. And that's where I want to point out a case study that we did, and it's a PhD work, and we are further implementing that concept. So let's take a look at the wholesale arbitrage. So the freedom in using the battery whenever you want to, and trade the power on the day ahead market. So you buy cheap the energy and you sell it expensive. And I mentioned earlier, when you use the battery, you're degrading the battery. And of course, there is a degradation cost related to that. So the model formulation is a key answer that allows, in fact, to implement increasing revenue and maximizing the lifetime of the batteries. There are multiple models that can be formulated. There is a bucket model, the equivalent circuit model, single particle models, which is physical model. And these degradation models are add-on on top of actually the way that you manage your asset and that you are operating your batteries. So we are quickly here comparing the degradation between prediction, so the way that models are implemented, and the degradation experiment in a very simplistic way. Okay, so we compare also the results of that with the performance in price of the arbitrage. So the conventional way to use the battery. So the battery is considered as a simple asset, and it's engaged or disengaged at the time that you need or that you don't need it, and that you have cheap electricity to buy and expensive electricity to sell. And the battery is considered as end of life when there is a 20% capacity decrease over the usage of the batteries. So this gives the degradation graph over the years. So this test results, we cannot share the brand of the batteries with you. It's confidential information. Nevertheless, what we see is that we have a compound growth in terms of revenue, or a stacked revenue, and the degradation cost is evolving over the time. When you add, when you care about the degradation and that you limit actually the capacity of your battery, for instance, to 80% instead of delivering 100% of the capacity of the battery, you can actually already take into account the fact that there is a reduction in the degradation over the time of the battery. So this is already a way to reduce from 50% degradation to 2.4 to 2.5% degradation. But of course, the revenue generation is lower, but the degradation cost is also lower. Okay. If you implement additional capabilities in terms of an advanced model system, you can actually leverage on the degradation, still the same. You can increase your stacking revenue, and you can maintain the degradation costs. So the modeling aspect allows you, in fact, with the physics-based model, the conventional approach, to reduce degradation to around 1.7%. So it's typical measurements that calculation and measure based on measurements, and the real measurements that we did at cell level. And the economic effect is that, accounting on the reduction or the reduction of revenue and the degradation costs, we can in fact increase the revenue by 17% against the accounting for degradation model, and decrease the degradation cost by 30%. So it is, from our perspective, a valuable solution to implement to improve the revenue and maximize the lifetime of the battery usage. To be also clear about where does the model come into the system. So the EMS is carrying the model in the system, and the BMS system delivers the parameters to feed the model. So it's really a very important relationship between the energy management system and the BMS system that needs to be implemented. So to conclude, because I want to highlight well, the fact that BMS is not something that it's not an easy material, in fact. And we started about 8 years ago looking into the battery management systems within Vito. And this is an incremental development that we did and that we implemented on top of the existing expertise that we have constructed on the hydrogen fuel cell stacks. And we migrated that into the battery sphere with lithium ion. So today we are at the second generation, and this is the mid part picture of the evolution of the BMS. And we are aiming, as Philippe Peters mentioned in his presentation about the battery, to the smart cell concept, which will be integrating some electronics inside the battery immediately in the battery cells to provide more intelligent systems, to improve safety and performance, to increase flexibility of the implementation, and to reduce the costs of the assembly of the battery systems in the future. And this is the end of my presentation.
Thank you, Serge. I have two questions. One that I've received in private. It's a little bit linked with material, but and I don't know if Philippe is still in the meeting, but I will ask you. Lithium-ion technology has a lot of difficulties to handle the cold. So why is it a good material to implement in cars, in fact? I see that Philippe is there. So the question is, if we use the good technology in cars right now, because they don't handle the cold easily.
Yeah, that's indeed the challenge. If you that needs to be further explored. If the battery materials nowadays will manage the temperature for automotive. As far as we can see, the things we're developing are capable of managing the whole temperature range needed for automotive, being also then in colder climates.
Yeah, but there is also the aspect related to the fact that the temperature of the battery is maintained to a certain level within the car, even if the car is parked. So that's the reason why the Tesla cars are still driving when it's minus 20 in the winter in Sweden and Norway. I mean, this is part of the story, and I can actually easily also highlight the fact that it's just a temporary concern. Look at the first generation of smartphones that were using lithium-ion batteries. People were using them during wintertime ski vations. And from time to time, there were some battery that were frozen, and the telephones, the GSM was not working any longer. Do you see that still today? No. Everybody is still using its smartphone when it's minus 10 outside, and in fact, it's still working even it's minus 10 outside. Okay, so I think it's a temporary concern about the characteristic of the batteries.
Okay, thank you. A broad question, but still very interesting from Marie from the CRIPS, so the R&D Center for the Ceramic Industry. What is the best CO2 vehicle in your opinion? So is there any cost target, for example, the cost of material per volume of CO2 that you can maintain, determining when technology becomes competitive? So it's quite broad, but
yeah,
very interesting.
No, Sergio. I think as a CO2 vehicle, and I understand this as a kind of a means to transport, to convey vehicle CO2. I think a conversion into methanol would probably be the easiest. It's a liquid. It's something that you can easily use and transport. Of course, it's a toxic material, so we have to be careful with that. But apart from that, I think that's something could be very useful material. Of course, it depends also where do you want to use it for. There are some industries are using some like methane or ethane already as a basic material. If you can convert immediately to that material that they use, of course, that's an easier way of kind of getting into the reuse of this of the carbon. So it has to be studied further, and it will depend on the different use cases. I think which one is the most
okay, thank you.
Profitable one.
Just a quick comment. A warm thanks to Serge for additional information about certification. So it's not a question, but I can say a warmly thanks to all the speakers of today. It's very precise and we have all the information that we needed. So very thank you for that. I will let my colleague, because we are on time for the end of the presentation. Renaud, maybe you can explain what is going on with the virtual visits during the lunch break?
Yes, so thank you everyone for this interesting discussion and presentations. The virtual tour will be presented by I think Johan, if I'm right. So I will maybe invite Johan to share the screen, and he will introduce you and present you the place that we will not see today, unfortunately, in EnergyVille in Genk. So we plan with Nathalie to organize a real visit as soon as possible. So once again, sorry for this. So yes, I think they have a very nice tour there, and I will let Johan presenting you all the different local and places that they have and organs. Thank you very much. Thank you, Cedric, also, and good lunch and good presentation.
And so for practical way, we start the visit right now, or we let a time for each one to get
the goal. No,
yes,
no. The goal was that the presentation of the tour is right now, and so yes, people can have lunch or doing whatever they want during the presentation, because it's unidirectional presentation so far. Okay, and so maybe we will meet at 1:15 to make the conclusion and last question or that can occur during this presentation.
Okay, but now I don't need a full hour to do this tour like this. That's a little bit too much, I think. But let's say in 15 minutes, I'll show you the highlights of the labs, and if necessary, you can always ask for more details later. I hope everybody can see this. This is the first time we're going to do a tour like this. We are actually experimenting with some new technologies, media technologies, also for education. So we've been making Minecraft models even of our buildings. But now we have something new. We used 360-degree cameras, and I can show you one. This is the GoPro version. These are cameras that take pictures on both sides with a kind of a fisheye lens. And then in software, this image is combined to a full 360-degree globe. So the picture that you see here, I'm actually moving that around with my mouse. You can see we can look at all sides. It's 360 degrees all around. Now, before you get dizzy, this is the building EnergyVille #1. EnergyVille #2 is over there. We'll go there later. The old mining buildings, you can see them on this side. This is the back side of the old mining building. On the other side, there's a really nice auditorium and conference center even. What you don't see is all the way in the back, behind the trees, there's the teaching and training center. Here is that incubator center for startup companies that Ronnie referred to in the beginning. So let's go inside the building. So I click on the link and then we enter the lobby. Now in the lobby, usually if there's a tour, we explain that the building is a BREEAM building. So BREEAM, it's not just about energy efficiency, it's about the full sustainability concept of the building. Of course, we are making a lot of green electricity. I'll show you that later. But for instance, things we also have to implement was recycling of water and the use of natural light. That's why we have always such big windows also in the offices, and there is no place, no office spot in the whole building that is further away from a big window than 6 meters. So everybody during the day can always work in natural light. We also have here you can see through in the lab. It's also very light there. That's because we have big skylights introduced in the building. Now the building is completely lit with LED lighting. You can see that on top here, and you will find in none of the rooms you will find a lighting switch. It's all sensor controlled, so if there's lots of natural light, it will automatically dim. If there's nobody around for a while, it will also dim automatically. So we never have to turn off or turn on the light. The building does that for us. Now let's walk around in the first floor, because I don't have a 360-degree picture of the basement. That is where the electrical cars are with the charge points. We still have to add that. But let's go to the first lab that we meet. This is the battery lab on the right side of the building. It's put there for safety reasons and also for easy access on the right side of the building. That's where trucks can also come on the yard and deliver goods. And here in the battery testing lab, this is before the expansion that will come now. You see on the right side, these are the cell testers. So in the back you find a lot of electronic loads and the equipment next to that are climate chambers. With these electronic loads you can perform as rapid cycle tests, fully automatic, and in the climate chambers you can do the associated thermal cycles for aging. As Sergi indicated before, we can do all kinds of tests, but not the destructive ones. It's not the goal that we blow up batteries in this lab. On the other side of the lab, this is all about modules. So you see there comparable testing systems, but they are a little bit bigger. That's because in modules, you stack the cells together, you put a BMS on it, and you do the testing then at their power and energy levels. This room is always nicely climatized at 25 degrees Celsius. So in the summer, it's nicely cool, and in the winter, it's nice and warm to work there. If we go out again, we'll go to the central part of the first floor. So this is the lab behind the entrance. Let's move forward to the initial part. So here you can see the entrance where we were a moment ago. And the first nice apparatus that you see there is our wave lab system. This is in fact a giant black box, but now the curtains are all open, so you can look through. And what you see there on the left side, I'm indicating that now, I hope you can see that, is a big it's a big multi-square meter LED light source. This light source can generate 1.5 sun equivalent. So we can put a lot of fake solar energy onto the solar panels that are put in the test unit in the middle. There's a second light source at the back that is for bifacial panels, because a lot of solar panels these days are bifacial, glass modules. So you also capture light, usually indirect light from the back. So to test that, you also need to be able to provide light from both sides. And that makes this test device unique. As far as we know, as far as I know at least, there is no second one like this in the world. So, and the solar panels in the climate chambers that you see here on the left and the right, they are prepared and aged for the tests. We do not only do the classical solar panels. What you see here, this stand-up module is in fact a module from a curtain wall from a high-rise building, and there we integrated different types of solar cells. In fact, this is a hollow module. By our colleagues from civil engineering, they have been studying how the ventilation works, how the cooling works with these modules, and the electrical researchers learned then how the temperatures of the cells are and where we can put the photovoltaic converters, so the power electronics inside these modules. And you end up with a plug-and-play solar BIPV module for big buildings. And we conceived it such that it can be plugged directly into the DC grid. Now, if we go further into the lab, it's a bit, let's see if I can walk behind here. Yeah, so we go behind that setup. What you see here is our RTDS system, so our real-time digital simulator. If I go from left to right, this is actually a system that emulates a highly dynamic electrical grid, because we also do high voltage grid research, and of course you cannot play with a real grid, so the only solution that you have is emulating it. So that means fast simulation, and in this box you have a parallel computer. It runs professional grid simulation software. The other racks, they are interfaces, and in the racks here, you have different types of input-output interfaces. There you can hook up typical grid devices. For instance, here in the middle, these are protection relays that are really used in high voltage grids. So in that way, you can test the performance of protection relays with a hardware in the loop system, and you don't have to blow up a real grid to test them. It's not only for relays, so fortunately it's hidden behind this panel, but we also test things like solar converters for voltage dip performance, fault right through, etc. The other devices are big amplifiers that help in the test. And the room next door is where system operators can come and do trainings, because you want people to train on an emulator, not on the real grid, of course. If we move out again, I turn around, there's another testing area for power electronics, and here we have one of the testing areas of the that's actually the high voltage lab, nicely protected, and there we can do the typical high voltage tests, surge tests, isolation tests, and so on. And this equipment can be connected to that grid emulator. So if you want, you can make, you can emulate a big short circuit there with hardware in the loop. Okay, if we move out, I came from there to watch out that I don't get lost in my own door. We were here, and then I had a link over here. Yeah, at the back side of the building, we have our thermal testing lab. It's literally behind the wall of that big electrical testing lab, and that is intentional because we see much more systems that are multi-energy, so they combine electrical power and thermal power, and in that way we can also make easy connections. Something that is not visible is that through the floor in the basement we can also make connections. There's lots of equipment in the basement. In fact, it's a sort of three-dimensional lab structure, so that allows you to efficiently use the volume and the space of the building. If you look around in this lab, you see lots of tubes there, and that is more common in the in thermal labs, and all of these tubes they are actually emulating different types of thermal grids. We have a steam line there, hot water line, several types of hot water line, hot oil line, so you can emulate all the generations of thermal grids. If you connect setups like the one you see here to these thermal grids, these are the equivalent of switches, but for hot water. There are several heat pumps in there, thermal storage systems. So in that way, you can test small hot water grids, thermal grids inside that lab. There's climate chambers in there for bigger equipment that allow you to test building elements in near real conditions. Okay, let's see if we can get out. Yeah, okay, now we went up one floor. I literally took the stairs in the corner there, and then we entered the home lab on the first floor. Sorry, actually on the second floor. The home lab, I'll take a quick look around, is a relatively long lab where we have all of those microgrids and related technologies. If I start left to right, we have our switching station, so the AC power comes in there, and with that copper switching matrix, we can lay out different we can reconfigure different cable systems, because I have to say maybe the most costly part of the whole lab is hidden below those floor tiles. These are floating floor tiles, and under it are several hundreds meters of different types of AC and DC cables. You can re-switch them into loops or long radial feeders from the switching station on. It supplies the AC microgrid part, and as you can see here, it's a relatively open area with lots of markations on the floor. That is because we are currently working on it, and it was cleaned up a little bit here for the photo, of course. But we are reconfiguring it to expand these microgrids. But the setups that you still see here, they are used for flexibility tests, demand-side management tests. And if you look well into the back here, you can see the smart meters that are being used in the Flanders distribution grids. All the types are in here, so companies can come here in the lab to test whether they are compatible with all the new types of smart meters, so that they can implement their flexibility services. And of course, we test that on real devices, hot water systems, washing machines, dryers, dishwashers, so we always have clean clothes and clean cups of coffees as a free gift. If you go further down the the lab. You see, this is a testing zone where we can see on the floor that there are several markations made. That is setups that need to return there. But this is the testing zone for the DC systems and the photovoltaic systems. So you can recognize some solar converters with battery systems in the back there. We do a lot of performance testing on them, measuring their real efficiencies, because don't believe too much of the efficiencies that manufacturers are putting on them. We have here an interface. This is actually literally the border between the AC and the DC part of the lab, because from here on we had the testing zone with all the DC equipment. It may look like an ordinary lab with tables to you, but I can tell you the technology that's in there is totally different. Every cabinet is a DC station where you can hook up loads, protection systems, and so on. It can go, as I said, up to plus minus 500 volts, but we also do the smaller things, like this is a 48 volt office setup that is also used in LED lighting. If I walk further, this is a typical lab where people working on power electronics are making a big mess. I can tell you this is not how it usually looks. This is way too clean. This is cleaned up specifically for the photo, but I can tell you normally people are soldering here and making power converters, the BMS systems, and so on. If we go up one floor, we are at the roof, and here on the roof, you can look around. We have, you can, if you want to, you can check the count on the photo, but we've got 1,078 fixed solar panels in different orientations and configurations of strings. Most of them are in some type of east-west configuration. The more flatter configuration, it's east-west, because in that way we have in the morning a bit higher production, and in the evening a longer production, and in the middle of the day the peak is flattened. This fits much better to our building energy demand, and also you can prove that this gives you the fastest payback on big flat roofs with the current prices of solar modules and converters. If you go a bit further, you can see that we have the flexible test racks. There we can quickly make setups. This is the perfect south orientation. So there they test so the more classical setups of solar panels. We gather the meteo data. They do reflection tests. You can see there are different backdrops here. That's for the bifacial panels. We have transparent and non-transparent modules with plastic backsheets or glass types. They're all being tested. They're accurately monitored. We literally produce terabytes of data non-stop in that setup. Of course, our fixed system is also closely monitored for performance and degradation all the time. This is the other corner of the building. The only spot that is not used for solar panels is this. That's our picnic spot on the roof. That is because the elevator shafts here, they give us a bit of too much shadow, and this is the north side, so you cannot put solar panels there. So we have a picnic spot over there, and a nice place to come with the visitors. Here, by the way, you can look around on the whole terrain. This is the whole Torpark. So as Ronnie mentioned in the beginning, we are housed on old mining terrain, and I showed you the mining tower in the beginning in front of the building, but here in the back, and this is roughly 1 kilometer away, you see the old terrils. So these are the artificial mountains with mining material. The whole area in between, it's several square kilometers, is now a science park and nature habitat. So it's always nice to do a walk in the lunch breaks. Building number 2 is over here, and here is the training center for technicians. And here you see our refurbished old mining buildings and the shaft, which is now a monument. Okay, but let's go down again, because we need to cross the square. So we quickly go down, we take the elevator, we are back into the entrance zone. Let's go out through the door, and we go to building number 2. You see, we had a different architect, so it looks a bit different. There's also, of course, a zone with meeting places, but behind this zone with meeting places and offices, it's in fact one giant sort of clean room. So if we enter there, now we have changed clothes. We are now wearing such a nice, comfy plastic suit, dust-free, and we are inside the clean room. Now, this is not the highest grade of clean room. It's not the kind of clean room where you can make microchips. This is a clean room that is intended to allow you to make solar modules, battery types, so the bigger types of electronics. Let's make a tour around the clean room. If we go through this door, we have here another room inside the clean room. This is a dry room. There you can make the pure battery materials, the electrode materials, electrolytes, and so on, the solid state electrolytes. Why is it a dry room? Water is the enemy of the battery, so you cannot have a single water molecule penetrating your battery, otherwise it will not perform well. So here the air is perfectly dry, and I can tell you, you literally feel that in your eyes. Normally we cannot go in here even with a visitor, so this photo is a rare opportunity to check these things. So you see here it's a quite modern chemical lab, and if we go out and we walk further, you see this is the rest of the equipment to finish off the batteries. It's a big chemical lab, in fact. And on the other side, we have the equipment to make solar modules. Let's see that I move in the right direction. If you go in this direction, here we have the equipment like laminators, or the equipment to handle glass sheets and glue them, laminate them. Here we can make our own small production of solar modules. So different types, for instance, with the cells produced by IMEC. Let's see if I missed a corner here. Yeah. This is the rest of the battery testing, the battery manufacturing lab, and also the lab. Sorry, this is the thin film section. Also, I'm a bit lost here, but this is the thin film section, and they not only make the standard silicon-based solar modules, but also thin film sections. And if you look here, it's a bit hidden here, and maybe I can come closer. Yeah, no, fortunately you cannot see it. Here you see actually a nice application of the thin film equipment. These thin films, you can make them so thin, or you can give them a bit of structure that they become transparent. And here is a demonstrator window where we can have translucent windows which produce electricity. So you can see you can push solar technology very far these days. Start with these cells, and the next question is then how do you put solar converters in the frame of the window? How do you connect them to the electricity grid? How you make a nice application for a building out of it? So I think here we have with the walk through the lab, we have literally walked through the whole value chain of a lot of these energy technologies that we are looking at, like the solar technologies, the source technologies. We have the full value chain across these buildings, the materials, the cell production, module production. Then the power electronics was in this building, system testing, system design, and then the whole building, which is a lab on its own. I told you about the BREEAM certificate, and this whole zone that we have here, this whole campus, including the historic buildings, is recognized as a sandbox zone. So we can always test out equipment here also on the public grid, where we have agreements with the regulators and the system operators to, for instance, test new business models, new types of grid support, and even new types of grid technologies, because it's between these buildings that we have a DC line to exchange power, as an example. Okay, looking at the time, I think I'm going to stop here unless I see something in the chat. Let's see. Okay, thank you for the compliment. Now this is just a 360-degree tour. We have, by the way, a version under construction with glasses, with these special Oculus glasses and glassball and Google Cardboard glasses. Then you have a better 3D view. But I invite you to come over and see the real operation of the labs, because if you ask me, these photos are way too clean. It's not representative for the hard work that's being done there 24 hours non-stop. Okay, thank you very much.
Thank you, Johan. Impressive way of making the tour. Due to circumstances, we really appreciate that we have...
It was the first time we ever did it.
All right. You have the movie, you have the pictures, you have everything.
Yeah.
So, and you can go around without losing your way. So very thank you. I've already received some thanks privately in the chat room, because some of the players have to leave the room. I don't know if there is some last question about the labs and the virtual visit that we have. It's now the time. Otherwise, I make the conclusion. So really thank you for the time that we have spent. We really appreciate maybe there is another, no, okay. We really appreciate it. This way, due to the circumstances, I think it's the best thing that we can provide today. It's virtually, but still a lot of information have been transferred, I think. For us, it's very important because we have to do the roadmap for our technological players for storage for the next years, and we want to provide as well as a cluster a way to go for this technology. We have done the same for hydrogen 2 years ago, and our objective is to do the same for storage. And so I really think it's very important to have this type of discussion between each other, because we can help each other in this technology. There is so much to do. I'm very pleased to have listened all the capabilities that you have. For sure, we will share a lot of studies that you have done and that you will do in the energy transition. Every time it's a pleasure to read it. And so we try to, as a cluster, to exchange and to provide this type of studies to the members. And of course, there is a lot of links with the projects. And I have an important reminder, but if you are a technology provider from Wallonia, you can play and you can have EnergyVille as a partner. We have already done some project between Wallonia and Flanders companies and R&D centers. Of course, the financial subsidies will come from the two regions, but still it's quite easy to do it. We have some examples right now between our members in Flemish project and the counterpart. So really, there is no border for innovation in the energy transition, and I think it's the big message here today. And maybe the final closing words, maybe for Mr. Belmans. I see that you are still on board with us, so I'll let you the final word.
Do you hear me?
Yes.
Okay, thank you for quote unquote being here and knowing that you're always welcome. What I do notice, and the more I see around in houses, is that everyone seems to be in a place where there are books at the back, although we're saying we are more and more working electronically. I hope it was a challenge for us, and I have to thank people from communication, especially in this case, Natalie, that it was set up. We doubted either it would be possible, but I think that we reach, say, at least 80% of the efficiency that you would have in the physical meeting. Probably you reach more people because it's not easy to make the drive, and it's easier to get into a telco. So there is the plus and minuses, but I think we did the best we could. And I fully agree with what you're saying. Yes, we can collaborate. Yes, we need to collaborate. Yes, we need all the brains there is. There's too much work not to collaborate, and 1 + 1 is more than 2, whatever the mathematicians may try to tell us. Always welcome. If you need something, let us know. There was a question on the hydrogen. That paper is already there. So go for it. Thank you, thank you, thank you. And always welcome. It's not far away. Au revoir et au plaisir.